Hey guys, welcome to 10.3. We are talking about parabolas today. So, first, of course, I want to talk about some uses of parabolas. So, your book tells an interesting story about how parabolas are used were used in the ancient Greek Olympic Games. So if you're interested in that, go ahead and read it. I'm going to talk about some other uses of parabolas. So again, parabolas are found by cutting a cone at an angle going through the bottom. And just like the other shapes we've talked about, parabolas actually have a focus. So this is my sort of badly drawn sideways parabola. But anyway, they have a focus. And it turns out that if light comes into the parabola, say the parabola is made of something reflective, right? If light comes in to the parabola and bounces off, then it's going to be redirected to the focus. No matter where it hits the parabola, it's going to be redirected to the focus, which is really useful because that means that we can take not just light, anything, sound waves, physical objects, anything will do this. So that means this is actually how satellite dishes work. Okay, so a satellite dish is a paraboloid. That's the fancy word for a 3D parabola. It's a very shallow one. So this is, say, the cross section of a satellite dish, and the focus is at the end of the antenna. So there's an antenna coming up from the satellite dish. And so all of those sound radio waves, or whatever waves satellite dishes pick up, are coming in, they're bouncing off the surface of the satellite dish, and they're being redirected to the receiver, which is at the focus. So that's one way that we can use parabolas, is receiving information and directing it to the focus. But it works the other way around too. If something is emitted from the focus and hits the parabola, it will bounce straight forward, always in a straight line forward. So if it's emitted, let me just erase these and then I'll redraw them. If it's emitted from the focus, then it will go straight out, which means that if we have a really good example of this would actually be a flashlight. Okay, there's a light bulb at the focus of a parabola, and then there's a paraboloid reflective cone. It's not really a cone, it's a paraboloid, right behind the light bulb. So you have this reflective surface, and you have a light bulb right here. And so when the light comes from the light bulb, it hits that reflective surface and it bounces forward. So you get the maximum amount of light going forward. And they do this in light bulbs, flashlights, and car headlights, specifically the older style, not the new LED style, but traditional style headlights, which a lot of headlights still are, will have a reflective paraboloid, and then a light bulb at the focus, and that sends as much light forward as possible. So the focus of a paraboloid can be utilized in two different ways. Either you're emitting something from the focus and that sends whatever that thing is forward in the fullest force possible, because it's sending it straight forward. Or you can be picking up signals or something, hitting it off the parabola, and that sends it straight to the focus. So one or the other works in either direction, in other words. But because of this, parabolas are super useful. So all that being said, let's go ahead and talk about parabolas. So we I can't talk. We know a lot about parabolas already. Like, you already know the basic shape, you already know the basic formula, but things we haven't talked about the parabola are the focus and the directrix. Those are the things we're going to be focusing on in this section. Focus and the directrix. This line, we don't often use the name of this line. It's called the latus rectum. And basically it's just the line that's parallel to the directrix that goes through the focus. So it goes straight through the focus and then the parabola at 2 points. And we will use interesting facts about the latus rectum to graph. So we won't be graphing the old-fashioned way, we'll be graphing in a little bit of a different way. And we'll be using information about the latus rectum to do that. I probably won't call it that because, generally speaking, I don't remember that that's what it's called. But yeah, so that has a name. You guys already know the axis of symmetry. The directrix is perpendicular to the axis of symmetry, and it's the same distance from the vertex to the directrix, from the vertex straight down to the directrix is the same distance as from the vertex to the focus. So that's going to be important, all right? In other words, the vertex is halfway between the directrix and the focus. If you're going in that, if you're following along the axis of symmetry. Okay, so we'll talk about that more. The definition of a parabola is that the distance from the focus to the parabola is the same as the distance from the parabola, as the perpendicular distance from the parabola to the directrix. So perpendicular distance, right? Because I could say, oh, well, I could go parabola to directrix over here, and then that distance is completely different. So we have to specify it's the perpendicular distance. So just like the distance from the focus to the vertex, a specific point on the parabola, is the same as the distance, the perpendicular distance from the vertex to the directrix, that's going to be true for any point on the parabola. So the distance from the focus to any point on the parabola is the same as the distance from that point, the perpendicular distance from that point to the directrix. Hopefully that makes sense. And then again, your book uses that fact to get the form of the equation for parabola that we generally use. This is centered at the origin, or not centered, vertex at the origin. Yeah, we'll talk about that more later. Okay, so you've been seeing this P popping up. It's in the equation. P is the distance from the vertex to the focus, okay? So then the opposite direction of that is going to be the distance from the focus to the directrix, right? So we have, this is P, this is also P. Just like we had A, B, and C with ellipses and hyperbolas, with parabolas, we have P. Now, so whatever is in front of the X is always going to be 4P. A lot of books call that A. This book just uses 4P. That's fine. Doesn't really matter. Yeah. So, yeah. All right. So continuing on, so let's look at the equations really quick. Obviously, these are going to be a little different if we're not centered, or our vertex isn't at the origin, and we will look at that. But I want to look at what is squared here. So if the squared thing is x, that's what we're used to, right? The squared thing is x. That is this type of parabola where we're facing up or down. That's the type of parabola we've done before, right? Because x is squared, that's what we're used to. If y is squared, then we're going to be facing right or left. Okay? So if y is what is squared, we're going to be facing right if it's positive p, left if it's negative p. So so if I had y squared equals negative something x, that's going to be my left-facing parabola. If I have x squared equals negative something y, that's going to be my down-facing parabola. So if I scroll down further, you'll see that. So that would be negative p, positive p, positive p, negative p. Okay? Y is squared, x is squared. So those are just things to pay attention to. Now I want to talk about this distance here. They have it labeled as 2p, which I agree with. But why is it 2p? Well, remember I said the distance from any, the distance from the focus to any point on the parabola is the same as the distance, the perpendicular distance from that point to the directrix. Well, here at this point, let's see how far we are from the directrix. We're in line with the focus, which means this distance is p, right? And then we also know that this distance is p. So here we are 2p away from the directrix, which means we must be 2p away from the focus. So when we're in line with the focus, we're always going to be a distance of 2p away. And so we're going to use that when we are graphing these. Okay? So that is, those are the basics on the equations. I want to get to the not centered at 0. Sorry, vertex not at 0. There we go. So vertex not at 0, same deal as before. We're going to have k minus something, h minus something, and instead of that being the center, it's going to be the vertex. So we've seen this before with vertex form of a parabola. It's just set up a little bit differently. But it's the same concept. Y coordinate of the vertex, x coordinate of the vertex, and so on. So it's pretty similar. And then of course you just go P from wherever your vertex is to get to the focus, and then the other direction to get to the directrix. So same deal. So I'm not too worried about that. I think you guys can do that. So I'm gonna stop talking, and I'll see you guys in the next video.